you find us this afternoon halfway through the engine build for Amy's 142, my old stage rally car that's going back to being historic road rally again. And it occurred to us that I've never mentioned what it is we do when we build one of our competition engines. So let's have a little discussion around that. There's only a handful of salient points that need saying. Let's start with when you choose not to build your competition engine. Okay, so when a car comes to us, obviously going into competition, many people are indeed focused on getting some high output motor, or at least higher output than standard. However, that's not the way to go about it if you're new to the business. Your car, first of all, to make it go from A to B faster, you want the suspension to be top notch. Basically our formula is Bilstein gas shocks, top quality polyurethane bushes, and a choice of our rally springs, or indeed fast road springs. So get your suspension sorted, and the geometry of which, just to remind you, the caster angle is very, very important on these cars. Get that wrong, the car feels like a dog. Get it right, handle beautifully. So you've got your suspension sorted, so that means dynamically the car is working. Next you want to stop, so get your brakes absolutely factory perfect. We don't like steel braided Teflon hoses. They're excellent in the track environment, which is very controlled, very little debris about. In the rally environment, all you need is for one of those braids to nick, and it will slowly work its way, and then you'll get a balloon of Teflon come out and the pipe bursts. The only brake failures we've ever known rallying have all been steel braided Teflon hose. So use original equipment, rubber hoses. Okay, so you dynamically we're sorted with the suspension tickety-boo. We've got this car to stop. Now before we start looking at more power, we also want to look at the back axle ratio. Now certainly the B18 wants a 456 back axle ratio, maybe even a 488 if you really want that sprintability. But a 4.3 or even a 410 is going to bog down a B18. It's just not going to be able to cope with that taller ratio. B20, on a Peking to Paris car, I would be tempted to go for a 430. But for a UK historic events, I'll definitely want the acceleration that comes from a 456 ratio. And then if you're really aggressive, then go for a 488. So that's the back axle ratios before you start building an engine. And the final thing, if your engine is halfway decent, then you'll get far more performance per buck spent by fitting an LSD, a limited slip differential, to the back end. Okay, so now we've got dynamically our suspension's done. We've got the car to stop reliably and consistently and well. And we've got our back axle ratio sorted out, as well as hopefully an LSD by this time. So you've now decided that really you've got to have more power. Well, let's go through what we're going to do. If you want the most power that can be wrung from this engine, then you're talking about a racer engine, and you're talking probably Mass Engineering over in Cambridgeshire. They can build you a true race motor. We're not into that. We're into rally. Our engines, we wish them to survive for years without rebuild, not races between rebuilds. And so therefore, we tone down a lot of what we do in the search for consistent reliability whilst giving extra power. Okay, Just let's quickly go around the ancillaries. So exhaust system, you already want to have pretty much defined, and that's going to be the 2-inch bore system. You don't need bigger than that. There's 2-inch bore is more than enough for any of the gases you can throw down it. We always go for the 4-into-1 manifold. Theoretically, that means that it's designed around redline power, whereas of course you may know already from my videos that I say it's all about low down torque, which should be a 4-to-2-to-1 manifold. However, the 4-to-1 has a nice 3-bolt flange, easy to split if you need to get into it quickly, and that to us is worth more than the marginal gains of going to a 4-to-2-to-1. So we go for the 4-to-1 simply for maintenance. That's the exhaust system. Carburetors. Talk to any of the sweet crews out there. Their heart will sink when they see a Weber because you know you're probably going to have problems. And if you see a pair of SUs, you sit there and go, that's going to work perfectly. Easy to keep going. So we tend to aim for SUs. Also, there's very little difference in redline performance. And certainly, I reckon no difference in mid-range performance at all. And indeed, in many Weber setups, we see the redline performance is poorer than SUs because they haven't been set up properly. SUs also have a certain ability to self-compensate at altitude. They will start going leaner as you rise simply because of the way they work. So to some extent, they will self-compensate for going rich at higher altitudes. So that's another good reason if you're going up and down 3,000, 5,000 meters. Then we put on a nice distributor. Of course, you'll possibly all know, to me, it's the 123 distributor that we sourced from Holland. And if you're going on the continent where you think you're going to have bad fuel, then you'll choose the USB programmable one, which allows you to switch between curves on the fly. Why do you want to switch between curves on the fly? If you pick up some bad fuel, then you'll want to go to a retarded curve to stop it from pinking. That's a lovely ability to have, and paid its worth well on the London to Cape Town rally. And finally, of course, you get far more performance per buck spent by reducing weight than you'll ever get from souping up your engine. So many people are running very heavy cars, and okay, it takes a bit of confidence for you to say, no, I'm not carrying a trolley jack, or I'm not carrying 2 starter motors, but that confidence comes as you gain experience, and you just have to spend your whole time thinking about what makes you competitive. And of course, the more weight you add in has 2 functions. It slows you down and it makes you more prone to failure. Both of those are just not what you want in a competition car. So when somebody tells you, yes, they need soundproofing in their competition car, you throw up your hands in horror and say, no, you don't. Listen to all those noises. They're telling you something the whole time. Enjoy listening to the noises of your car. I think we're now ready to talk about what I do to the engine. Now we've said when I don't do anything to it. Okay, we're halfway through here, for which I apologise. So what have I done? This block has gone away to the engineers, so just as usual, it's been bored to the new pistons. The crankshaft has all been ground to the correct bearings, and that's pretty much where we're at. So in goes the crankshaft. Then we take the reciprocating masses. Now, we like Marler pistons. If you can get them, we would just stick with a stock Marler piston. Their weight always appears to be very close to each other, within 2 grams, which makes life easy for the next stage, and they're high quality. If you can't get hold of the genuine Marler pistons, then we also supply forged pistons as well. And you get your set of 4, and your first task is you're going to get your scales out and weigh each of them. Don't bother getting the rings with it. I mean, if the rings are already fitted, then fine, make sure they're all weighed with their rings, but if the rings aren't fitted, do it without them. So we get each of the 4 pistons and gudgeon pin and weigh it. Then, in pencil, put the weight on the crown and set aside. Next, arrange them in weight order, from lightest to heaviest, and mark them A, B, C, D. So we now know the exact weights within 0.1 of a gram of each of our pistons assemblies. Because what we're going to do is we're going to make sure the entire reciprocating mass is balanced up to within 0.2 of a gram. So you're then going to put each of number 1, 2, 3 and 4 conrod assemblies onto your scales and weigh those and label those down, 1, 2, 3 and 4. And now you're simply going to match the heaviest piston with the lightest conrod assembly, the lightest piston with the heaviest conrod assembly, to try and even out all the weights. Then write down that total reciprocating mass on 1, 2, 3 and 4. Circle the lightest assembly, and now your task is to carefully remove weight from each of the other 3 to match that lightest. And what you do is you take your flapper wheel and, looking at where the casting flashes are, down the side of the conrod, the end of the cap conrod, and to some extent on the top of the little end as well. And you're going to carefully polish that down, each of them, as far as you need to match that lightest weight. Here you go. That's the flapper disc that I used for this task. In my case, it's 115 mil diameter, and you've just got these layers of abrasive paper. And that takes off the metal surprisingly quickly. Okay, so we now have a set of 4 reciprocating assemblies that are within, well, aim for 0.1 of a gram, but settle for 0.2. So in that goes. What I didn't mention earlier is that we always balance the rotating masses separately. So we'll have the crankshaft balanced by itself, then the flywheel will be balanced by itself, and we do not balance the clutch assembly, because the clutch assembly is going to change several times during the lifetime of this engine. So therefore we want everything balanced independently, excepting the clutch. Okay, so now we have the pistons in. So onto camshafts. In my youth, running around in Escorts, either RSs or Mexicos, we regarded 270 cams as very wild, giving you a very unpleasant idle, but with the gains that a 270 gives you higher up the rev range. These days, camshaft technology has moved on significantly, and you can run a 300-degree cam with a sensible 800 RPM idle. Although a caveat there, if you look at Richard Iskandarian's instructions on his, he does very clearly point out that you want a 1200 RPM idle for longevity of the lobes. So although it will idle at 800, do not be tempted to. run it, as Richard says, at 1200 RPM to keep the end lobes lasting well. Now, we've gone through various guises. We know that the 310 cam works very nicely in a fuel-injected engine and also with Weber DCOEs. However, the 310 with SUs, the SUs will tend to throw fuel out of the reservoirs because of the massively unbalanced vacuums at idle. So we come down to a 300 degree or less for the Amazon. Now we are parting with our knowledge of the 300 camshaft and the 280, which is what we've traditionally recommended to our customers. And in this Amy's engine, which is basically one of our in-house competing cars, we are going with Richard Iskandarian's recommendation for this new camshaft. He reckons we should be trying this. I gave him our desires from a road rally car, which is that we want low down pulling grunt, we're running twin SUs, and I want a 7,000 RPM red line. And given those three factors, he then suggested that we try this camshaft rather than the one we've been running for years. So let's see how that one goes. So we've chosen our camshaft, that's going to go in. So having chosen your camshaft and built your engine, do not forget to make a clear note of what camshaft is in this engine. Now this is critically important if your car ever goes to somebody else to be serviced. And in addition to labelling down what the camshaft is, I'll actually give them the tappet clearance as well. Now, in theory, on all our engines, this is going to be hot or cold because it's an iron block with an iron head and it's a steel follower with a steel push rod. So everything's expanding at the same rate. Therefore, it doesn't matter whether you measure that tappet clearance hot or cold. Okay, so as I say, always put a very clear label, preferably one that can't be rubbed off, saying what the camshaft is and what the valve clearance is as well. There we go. All just makes life easy for the future. Now let's look at the other source of rev limitations on this engine, which is of course the valve train, specifically the follower and the push rod. Now the standard engine comes with this very nice and reliable follower. It has one slot for lightness and for lubrication. Oil tends to build up in here and provide the lubrication as well, so it does two functions. And the standard solid push rod. Now that's good for 6,000 RPM. You can consistently hit 6,000 RPM with the original setup like so. With any slightly more interesting camshaft, like we used to run, and still do occasionally, run a K-cam, which is pretty much the same as a D-cam. We can't tell the difference between the two in terms of performance. With that camshaft, you can reliably hit 6,500 RPM and still be pulling. However, of course, at 6,500, that is where you're beginning to get your valve chatter, your valve spring chatter, as the whole unit tends to launch off the cam and then bounce back onto the camshaft. And for that type of an engine, we then cross drill our follower to make it lighter, and therefore it doesn't launch off the camshaft. So that gives you a straight 6,500, quite possibly 7,000 RPM on a standard lift camshaft. And we still stick with Volvo solid rods. With our high lift, that's half-inch valve lift camshafts from Richard Iskandarian, we do actually use the recommended ISCI followers and push rods. So there we go, that's our component ISCI follower, like so, and we mate that to one of ISCI's tubular and therefore stronger push rods. So the Volvo original equipment setup of follower and solid push rod is 131 grams. 131. When we go to the cross drilled, we drop that for a 6,500 RPM red line, possibly a 7,000, down to a 123 grams, 123 grams. When we go for the Iskandarian follower and tubular push rod, then we're up to 141 grams. So you say, why am I fitting heavier weight? Well, one aspect is that at 7,000 RPM, I do not want to have any concept of my push rod flexing, and therefore we go for tubular, which is of course considerably stiffer than Volvo's solid rod. Okay, that's one reason, but to be honest, we can get tubular OE length push rods, so that's not it. It's really that given that we're using ISCI camshafts, if we have an issue, which we haven't had yet on any car, neither ours nor a competitor's, then I can say to Richard, we are using his camshaft, his follower, his push rod, and his twin spring valve retention. However, being absolutely clinical about this, I think we really should be going to our lightened followers and the OE length tubular push rod, which of course will give us the best of both worlds. So yeah, that's an argument. I'm not sure. I think at 7,000 RPM, I kind of like ISCI's lifter in there for strength. So to summarise, we fit a distributor that can cope with over 6,000 RPM, which a mechanical can't efficiently. And then the valve train for any 6,000 RPM engine, quite happy to use Volvo's original follower and solid push rod. K-cam or similar with an expectation of 6,500 RPM, definitely go for the lightened follower and Volvo's original push rod. 7,000 RPM, we go for the uprated lifter and a tubular push rod, and that will give you 7,000 RPM. So on the topic of cylinder heads, do try and discourage your machinists from spraying paint on these machine surfaces. It doesn't really matter that it's on the fuel injection boss, but you don't want paint on the seat of the cylinder head bolts, because of course that means you're talking down against paint, not against metal. And why do we use cylinder head studs instead of the original cylinder head bolts? There's only one reason. There's one reason not to. These of course are adding weight, which you don't want to do. However, what it does mean is that you can torque down more accurately than with a bolt. With a bolt, you're never quite sure it's not the scale inside the thread that you're torquing against, rather than the pressure against the head. Whereas at least with a brand new set of studs, you know that's a clean thread, you know your nut's got a clean thread, you know you've got no paint on the seat, on top of the head, and therefore the torque you apply to the nut is the torque you're applying to the cylinder head gasket ultimately. So that's why we use these. The cylinder head bolts are plenty strong enough, they're plenty man enough for the job, It's just that you can be absolutely dead certain that the torque you apply to here is the torque that gets applied to the cylinder head gasket. Neoprene seals. Okay, so the front and rear crank seals in the early cars, all the B18s and most of the B20s, had a felt seal front and rear. Volvo then introduced the neoprene rear seal, but left the front seal as felt. Now we now run neoprene conversions both front and rear, but I have been questioning recently as to whether that's right on competition motors. We have found time and again that the sort of revs, basically our 7,000 RPM red line, I think causes us problems with particularly the rear neoprene, because the surface is travelling about twice the velocity at the neoprene than the front is, simply because it's twice the diameter. And I don't think the neoprene can cope with that. So I'm not totally convinced that neoprenes are correct for competition engines. I think it's possible you would fit felts and aim to replace them once a year, for instance, which can be done in situ quite nicely. But as it happens on Amy's engine, I've chickened out and I've gone with what we know, so it's sticking with neoprenes. Okay, so that's all the trick stuff we do down the bottom end, which is all very simple stuff really. Let's have a look at the top end then. Now, I have been thinking for well over a year now that I'm not sure gas flowing of our cylinder head is worth the effort. It's moderately expensive, it's certainly more than £1,000. And yes, there's no doubt about it that at the top end, the red line, 6,500 RPM to 7,000 RPM, it's got to be noticeably more powerful than the standard cylinder head. However, at the bottom end, the theory is that it will be poorer performing, because what you want is high gas velocity. Gas velocity is directly proportional to the diameter of the intake tract. The smaller the diameter, the higher the velocity. The larger the diameter, the lower the velocity. When you gas flow ahead, necessarily, you are taking metal out, not adding it in, and therefore you are reducing gas velocity. So therefore, your bottom end and mid-range torque is poorer on a gas flowed head than it is on a standard head. And for this reason, I haven't gas flowed Amy's head. I still have my old gas flowed head, which we've set aside in case Amy finds that we are down on power compared to what we expect to see out of these. But we're just going for a high compression. Now, high compression to me is 12 to 1. You can wind these up to 14 to 1, and that's fine, but we go for 12 to 1. Not least of all, we've got to be aware that probably owners may well take a couple of skims off the bottom of the head during its lifetime anyway, and we don't want to run out of usable metal on the head. Now, this is a 2-litre engine, and specifically this is the big valve 2-litre. The earlier 2 litres had 42mm inlets, these have 44. Now, would you like to know how you tell the difference? Let me show you. Can you see these P-shaped castings on top of the head here? Number 1, number 2, number 3, and number 4. These are the castings for the fuel injection motor. So that would be drilled and tapped. This is the injector orifice, goes through into the inlet tract. And therefore, you know that anything that has a head with these P-shapes on it has got to be a 44mm inlet valve, so a big valve head. If in fact these P's do not exist at all, you know you've got what started off as a small valve head. So in the 2 litre, the 42mm inlet. Now, the chamber on the 2 litre head is identical. So in fact, you can, there's no reason why you shouldn't machine the head to accept the 44mm valve and make a small valve into a big valve head. That's absolutely perfect. There's no argument against that at all, really. The B18 head, however, is what it is. If you try going big valves on a B18 head, all you do is start shrouding it by this bit of combustion chamber here, and you'll find probably you've got less inlet valve swept area than you started off with the smaller valve. So don't go messing around, it's my opinion, with B18 valve sizes. You will not improve it, and you will probably make it worse. Good, that's that. So the other thing to note on here is these are not the standard valve springs. These are dual spring. And the reason we have these is no other than the fact that our camshaft is 1/2 inch high lift. When you depress the valve by 1/2 inch on the standard single spring, you get spring binding and you will get an early failure of the valve. It will simply part company from its stem head and trash your motor. So by going to twin valve springs, we can then get that full 1/2 inch high lift. And high lift, of course, means high torque motor. So that's why those are twin spring. And then there's your choice of gaskets. We now use L-ring, which we have never had a single issue with. So we like L-ring gaskets, that's what we use. Now what about, in conclusion, overboring these? Now obviously look at your regs, but if your regs permit, then actually you can even take the B18 block out to 2.1 litres by using the B21 2.1 high compression pistons. We've done that on Emma's road car, and that's still running. B18 2.1 litre. Obviously you have to use a 2 litre cylinder head, otherwise the compression ratios will go through the roof. It'd be more like a diesel then, back to its origins. So you can do that if that's what you want to do. We actually rather like the stock B18, maybe with plus 60s in there. It's such a spinny engine. It'll rev over 7,000 RPM if you get it right. Yeah, we wouldn't tend to overbore like that, but you can do it. And then of course, your other option is to go stroking the engine. Again, not something that we've ever wanted to do. Again, because we like the revvy nature of this. As soon as you start stroking it and giving it a long stroke, you're going to lose that revvy nature. 7,000 RPM, probably not available to you anymore. But on the other hand, load of torque. But yeah, we don't touch that, but it's possible. Flywheels we haven't talked about, only briefly earlier. You have a choice of flywheels. The original flywheel is of the order of 12 kilograms. Well, that's, it means almost impossible to stall the car at that weight. We go for lightened flywheels, which is just taking some of the metal off as much as we can, which takes it down to a 10 kilo flywheel. Probably for most people you wouldn't notice the difference, except the fact that it accelerates better. There's a scalloped flywheel, which allows you to take a bit more metal out than simply lightening it, but is more elaborate machining process because you're going in and out And that'll take you down to 8 kilograms, which again really has no effect on idle speed. You'll still idle at 800 if that's what you want, if that's appropriate for your camshaft. But now you're getting into significantly better acceleration abilities. And finally, there is this. So this is our billet flywheel that we have made for us. That's 5 kilograms of flywheel, and just gorgeous. It's so lovely. We've run that on my 142 for quite a few years now, actually. And again, you can get that idle down to 800 even with a 5 kilogram flywheel on it. But at Yiski recommendation of 1200 RPM, it's absolutely perfect, and that really does fly up. But of course, if you've got hill starts, you've got to be a bit more sensitive on the clutch. And if you've got hill starts with a 410 axle, you're going to probably end up burning out your clutch fairly quickly just by trying to spin it up too much. Again, another reason why you get your back axle ratio right to begin with. That really is it. That is Amazon Cars competition engine. Forgive me for sounding as though it's all simple. It is. We're not trying wacky things. There's all sorts of strange theories out there that change from one decade to the next. Our engines are quick. They're certainly top 3 finisher quick. We've proven that with the Rally of the Tests for a start, when Dan Willen won it outright with one of our engines. But we keep it simple, we make it fun, and it stays reliable. That is the 3 things we want to achieve, and I think we've done it. We keep changing gently our process, like this theory of going away from gas flowed. I hope that process will continue, that we'll still pay an intelligent attention to what we think about these engines and where we can make benefits, or where benefits just aren't there to be had. But there you go. Competition engines from Amazon Cars. Thank you very much. We'll go out and finish the build on Amy's and send her out competing. Thank you.